Okay, kinetic molecular theory. We've talked a lot about gas laws. Laws say what happens. Theories explain why those things happen. So this is the simplest good model for the behavior of gases. It's called kinetic molecular theory. It's explaining gas behavior based on molecules and how they move. How do the gas molecules move? What are they doing? So we're modeling the gas as a collection of particles. Those particles may be molecules or atoms depending on the gas. And they are in constant motion. So keep in mind a picture like this in your head. You've got little molecules and they're just zinging around, bouncing off the walls. Okay, this reminds me of the old computer game Pong, where you had this little blip on the screen and it would just bounce around. And gas molecules are a lot like that. So here are the ideas in the kinetic molecular theory. The size of a gas particle is negligibly small. Gas molecules do have volume, but they are so small compared to the overall volume of the gas that we can just disregard their volume. So gas particles are assumed to have no volume, but they do have mass. So if we look at STP at argon gas, the actual atoms occupy 0.01% of the gas volume. The rest, the 99.99% of the argon gas at STP is nothing. It's empty. So that 0.01% we can just leave out of most calculations. It's just not important. It's literally a drop in the bucket, right? You got a big 5-gallon bucket of water. You put one more drop in it. Does it really matter? No, it doesn't. It's too small relative to the whole thing. If an argon atom was the size of a golf ball, the nearest neighbor to it in a gas at STP would be 4 feet away. So there's a lot of empty space. Average kinetic energy of gas particles is proportional, directly proportional to the temperature in kelvins. As you raise the temperature of the gas, the average speed of the particles increases. Now, it's important to note that this is the average speed. So just like with so many other things, you could say the average IQ or the average family size or the average height of a person, right? There might be a couple people that are actually on the average, but most people are above or below. Well, we can look at increasing the average, decreasing the average, but not all of the gas particles. I didn't see that yesterday. I didn't know that gas articles shouldn't be moving at all. Oh my goodness. Gas particles. Not all the gas particles are moving at the same speed, but the average is related to the temperature. When particles collide with each other or with walls of the container, it's a completely elastic collision, meaning that there's no overall loss of energy. They may transfer energy, but they don't lose energy. And when we think of objects that are large enough to see, we can look at something like a collision between billiard balls. Nothing that's large enough to see is completely elastic in its collisions, but these are pretty close. If you shoot one ball and another ball at each other, when they collide, they will bounce off and they will keep moving, right? And the amount of, or their velocities will be roughly the same. They will transfer energy, but they don't lose it. If you look at 2 lumps of clay being rolled together, they're just going to go and stick together, right? They're not going to bounce off of each other. What happened to their kinetic energy? It gets dissipated as heat. So when these 2 lumps of clay collide, the kinetic energy that they had from their movement is gone now. It's not kinetic energy anymore. It gets turned into heat energy. which is then just, just kind of lost. It's not very useful. Any questions about that? Because the gas particles do not lose energy when they run into things, they never stop. They just keep going. And that's not something that we see on the macroscopic level, right? You roll a ball across the floor, it's eventually going to stop because there's friction. But what are those gas particles moving through? Are they moving through air? No, they are the air. They're moving through nothing. There's nothing to slow them down. When they bump into each other, they retain all of their kinetic energy. So how does this explain gases? Well, we talked about pressure being force divided by area. So the gas particles are constantly moving, and so they're going to strike the walls of the container with a force. It's a small force, but there's a lot of gas particles, and they're moving pretty quickly, and so they're going to hit the sides a lot. The result of the many particles hitting the surfaces around them is what gives us a pressure. So the area would be the area inside the container, and the force would be the particles hitting. So that's how gases exert a pressure. Oh, I was going to change this. I don't think this is a correct picture, so just ignore that. Boyles Law. Boyles Law says the volume of a gas is inversely proportional to the pressure. So how does kinetic molecular theory explain that? If we take the volume of a gas and force it into a smaller volume, what happens to the molecules in their collisions? They're in a smaller area, a smaller volume now, and so they're going to collide with the walls more frequently. So think of a room full of kindergartners, and they just had cupcakes because it was somebody's birthday, right? And so they're all wired on sugar. And the teacher stepped out for a minute, and they're going nuts. They're just like running around like kindergartners on sugar do. So they're going to bump into each other. They're going to bump into the walls. They're just, there's going to be some collisions. If we contain them in half of the room, same number of kids, same energy level, they're going to run into each other more frequently, right? Because they're more crowded together. That's like what gases do. So you take a gas and you cut its volume in half, but its kinetic energy is the same, there are going to be more collisions with the walls. And so the pressure will increase. So you increase the pressure, the volume has to decrease. You increase the volume, the pressure decreases. It's an opposite, inverse relationship. Any questions? My big question is, where the heck did I get that picture, and what is it supposed to be for? I don't know. Charles' Law. Volume of a gas is directly proportional to absolute temperature. So kinetic molecular theory says if we increase the temperature of a gas, we're increasing the average kinetic energy. So if we increase the average kinetic energy, that means that the gas particles are moving faster. Anybody know the equation for kinetic energy?
1/2 times mv squared.
1/2 times mv squared. So kinetic energy is equal to 1/2 the mass of the object times the velocity, its speed, squared. Well, the mass of these gas particles is not going to change. If we heat them up, the kinetic energy increases, the velocity increases. So you've got gas molecules moving faster. They are going to collide with the walls more frequently and harder. Well, in Charles' Law, we had constant pressure. So how could we keep constant pressure when the gas particles are moving faster? We have to spread them out. We have to increase the volume so that we can have a constant pressure. So you increase the temperature, the gas will increase in volume if the pressure is constant. Does that make sense? Avogadro's law. I guess let's go back to this for a minute. So if we're keeping with the kindergarten analogy here, what's happened here is increasing the temperature. You've increased the energy level of these kids. You maybe gave them like Rockstar or something, which would be a very bad idea. Right? So they're like supercharged now. They're running around the room. They're running into each other. How can you reduce the number of collisions? Spread them out, right? So you open up the adjoining room and you increase the volume, and now you can keep the number of collisions the same. Didn't mean to do that. Avogadro's law. Volume is proportional to the number of gas molecules. So in the kindergarten analogy here, what you're doing is you're putting more kids into the room. You put more kids into the room, you want to keep the collisions constant, you're going to have to expand into the next room again, because otherwise they're going to run into each other more frequently. Increasing the number of gas molecules has more of them hitting the walls, and so the pressure would go up. If we want to keep the pressure constant, we must let the volume increase. Dalton's law of partial pressures. The total pressure of a gas mixture is the sum of the partial pressures. Well, kinetic molecular theory explains that the particles have negligible size and they don't interact with each other. When they run into each other, they just bounce off. They don't lose any energy. They don't stand around chatting, slow down, nothing like that. Particles of different masses still have the same average kinetic energy at a given temperature. The kinetic energy is related to the temperature. The mass does not affect the kinetic energy. So we've got different masses of particles. Maybe we've got nitrogen and oxygen gases mixed together, but the kinetic energy is the same. And so the total pressure of the collisions is the same regardless of what gas it is. So the nitrogen does what it's going to do. It's going to run into the walls, and the oxygen's going to run into the walls. And it doesn't matter what particle they are. They all have the same effect. So the pressure of the nitrogen plus the pressure of the oxygen gives us the total pressure. Kinetic molecular theory predicts behavior of gases that is consistent with our observations and our measurements, consistent with the simple gas laws and consistent with the ideal gas law. The model does break down under certain conditions, but by studying those, we can actually learn more about gases. So let's look again at the temperature and velocity relationship. So kinetic energy is 1/2 mv squared. Gas particles at a given temperature have the same average kinetic energy. Well, if some of them have smaller masses, then they must have higher velocities. And the ones with the larger masses have smaller velocities. My kids play football. There's a guy on my son's football team that's about the size of a refrigerator. I mean, he's just very impressive. But he can't run very fast, right? And that's kind of typical. You got a really big guy, they can't run very fast. And then there's some other guys that, you look at them and you think, you're kind of scrawny to be playing football, but those guys are fast, right? They're very successful because they're so quick. So the same idea with gas particles. The big ones are going to be traveling at a slower velocity. The small ones are going to be traveling at a higher velocity. When we talk about velocities for gases, we usually use the root mean square velocity. It's a special kind of average, and we don't need to go, and we don't want to go into why is it different than just an average velocity. It's really close to the average velocity But there it is. It's just a little different. But this means velocity. It's the root mean square average velocity. So the kinetic energy, the average kinetic energy is 1/2. This would be Avogadro's number, and the mass of the particles, and the root mean square velocity squared. So we already talked about this. Lighter particles travel faster than heavier ones at a given temperature. And so this is the equation. The root mean square velocity of a gas particle is equal to the square root of 3RT over m. R here is the ideal gas constant, but the units are different. And so the number is different. You do not need to memorize this number. If you need it on an exam, I'll give it to you. 8.314 joules per mole Kelvin instead of liter atmospheres per mole Kelvin. And then m is the molar mass. The molar mass there has to be in kilograms per mole so that the units work out. I'll give you this equation also, but you need to know what it means, right? What the T is and what the M and the U and all that junk is. So we should be able to do a problem like this. Calculate the root mean square velocity of gaseous xenon atoms at 25 degrees Celsius. So the root mean square velocity, URMS, equals the square root of 3RT over capital M. So R is the ideal gas constant, but it has different units. It's 8.314 joules per mole Kelvin. A joule is equal to a kilogram times a newton. And a newton is
Measure of force.
oops, that was wrong. Yeah, a newton is measure of force. Oh, I'm blanking. It's m squared, meters squared per second squared. I think it's kilograms meters squared per second squared. So then, if we put those two together, a joule equals a kilogram times a kilogram, which would be kilograms squared, meters squared per second squared. We'll see if I did that right. I did it different yesterday. Okay, so we need 3. That one's easy. 3 times our keep using the wrong end of the stylus, and it's supposed to work, but it really does not. Times the gas constant there, times the temperature. 25 degrees Celsius, we have to put that into Kelvin, 298.15 Kelvin. And all of that will be divided by the molar mass in kilograms of xenon. So xenon's 131.3 grams per mole. We need it in kilograms per mole. So if we convert that, 1 kilogram is 1 times 10 to the 3rd grams. We end up with 0.1313 kilograms per mole. Yeah, those units are bothering me. Something's wrong there. We'll figure it out. Kilograms per mole. And then the square root of the whole mess. So let's get the number first. On my calculator, the 36X Pro, I do the square root symbol first. And then I've got 3 times 8.314 times 298.15 divided by 0.1313 equals, and I'm getting 237.986. How many sig figs?
4.
4's a good guess. Close.
3.
3. See the temperature? It's only got 3. Units. Well, we see that the kilograms cancel. The kilograms. The kelvins cancel. And the moles cancel. And so what we end up with is joules per kilogram. I should have done it the way I did it yesterday. Joules per kilogram. Okay. We have solved the problem and found out where I made my mistake. The Newton is a kilogram meter per second squared, not meters squared. And a joule is a Newton meter. Meters times a Newton. So then we end up with meters times Newton. Here's the Newton. When we multiply these, we get kilogram meters squared per second squared. So when we put that in here, we've got joules per kilogram. The joule is a kilogram meters squared per second squared. And it's divided by kilograms, so kilograms cancel out. Then we have meters squared per second squared, and we're taking the square root of that, and so this unit comes out to be meters per second. You probably would have preferred me to just say, the units end up being meters per second, don't worry about it. But there it is. You do not have to know what a joule and a Newton are in terms of other units. But this ends up with a unit of meters per second. Is that fast? 238 meters per second? Yeah, that's really fast. So xenon gas at room temperature, the individual atoms are moving on average 238 meters per second. They are zinging around. Gas molecules are moving fast. Any questions?
Did you times it by the kilograms, that second part?
Up here, you mean?
Yes.
Okay, so I crossed out all the units except for joules and kilograms. So I had joules on the top and kilograms on the bottom. Down here, I figured out that joule was equal to a kilogram meter squared per second squared. So I have kilogram meter squared per second squared, and that's divided by kilograms that didn't cancel out. The kilograms cancel each other here. I end up with meters squared per second squared, but all of this is inside the square root, and so I get meters per second.
I have a question.
Uh-huh.
How come when doing ideal gas law, R equals 0.08206?
That's a good question.
Could you use like an R like subscript, something else, just to, because both R and both equal?
Well, they're both R because they are the same quantity. When you change the units, you change the number,
Oh, okay.
right? So it's not that there's two different
It's just
ones.
it's
It's just the units are different. Now, if you used 0.08206 liter atmospheres per mole Kelvin in here, your number would come out different. The units would not work out nicely. You'd have to do some unit conversions to get to somewhere useful. Atmospheres, there's actually a a conversion between atmospheres and liter atmospheres in joules. A liter times an atmosphere is a unit of energy, crazy enough. So, but I won't make you memorize this one. I have a hard time remembering it myself. Let's make sure I didn't skip anything. Okay. No, one of these is wrong too. Oh well. Okay, so what we see here is we have relative number of molecules with a particular velocity graphed as the velocity increases. And so what we see is that oxygen, nitrogen, water, helium, and hydrogen. Oxygen here is the largest molecule, the highest molar mass. Hydrogen is the smallest of these. The oxygen molecules being larger at a given temperature are going to have a lower average kinetic energy, a lower average velocity, because they all have the same kinetic energy. So the velocity for the oxygen is lower. It's, I don't know, maybe 350 or so, average. Hydrogen's average velocity is around, I don't know, 1700 or so. Higher average velocity. But in addition to that difference, what we see is that as we get higher and higher average velocities, we also see a wider distribution. And so for hydrogen, there's a lot more variation in what those velocities are. Overall, the average is higher, but there's a lot more variation. So if we were calculating standard deviations, this would have a large standard deviation. Oxygen would have a small standard deviation. So as you increase the velocity, as you go to smaller and smaller particles, it's spread out more. If we take a single gas sample and heat it up, so maybe this is oxygen, at 273 it has this distribution. So it's a pretty tight distribution. All of the velocities are within this range. As we heat it up, the average velocity increases. And as the average velocity increases, it spreads out as well. The distribution spreads out. So then you've got, nothing else to say about that one. Any questions?